speaker of this second morning session is Professor Sinya Aoki from IITP in Japan. And he will tell us about hadron interactions in lattice QCD. So, please start.
Yeah. First of all, I'd like to thank the organizer for inviting me to this workshop. I'll talk about some lattice QCD approach to the hadron interaction. So, in particular, our approach we call HARQC is the name of our collaboration to the nuclear physics. It's as follows. So, our task is first calculate hadron-hadron interaction, in particular in terms of the potential in lattice QCD, and provide this information to the nuclear physics, or to determine direct calculation of the nuclear physics using this potential, or provide information of the parameter in the effective cell. Then this information also can bring some new property of the neutron star or supernova explosion. So some word is from QCD to cosmology or astrophysics from star. So this is our task to calculate interaction in terms of the potential. So this is the plan of my talk. I first explain our strategy in more detail and give some recent result, which is must be selected one. First one is some diversion, and the second one is some exotic state for candidate with the SC3900, and give some summary. So let me explain our strategy first. So there are several references. If you are interested, please look at these. And let me explain the strategy. The first, we consider so-called equal time non-base salvator wave function, which is defined in this formula. So we consider QCD eigenstate, and it is the two nucleon operator at x and x plus r. Since it's QCD, we construct this nucleon operator in terms of three quarks, like this scalar singlet object. And in our definition, we use some so-called local operator. Local means quark is also same point x. You can use different operator which correspond to different scheme, we call, like MS bar scheme or MS scheme. And we send it to the vacuum. So this quantity depends on relative coordinate r, and also some energy or relative momentum k. From this energy is, of course, this relativistic energy 2 times square root of k squared to mn square. And in our approach, we assume this energy is smaller than threshold, pion production threshold. Therefore, we only consider elastic scattering. Of course, the extension to the inelastic scattering is possible, but still, in this talk, I keep this condition. So we consider NN to NN scattering. And the main idea is as follows. So we consider some box size there. But this box must be larger than interaction range of the QCD. And this is the assumption. We assume QCD interaction is short range, which is cut by pion mass, effectively pion mass. And therefore, this region's interaction is almost negligible. And theoretically, we can show that N-base wave function can be written in this region as a sum of the partial wave, like this. But important point is we have some phase shift delta L, okay? But this phase shift is related to the asymmetric of the QCD, not quantum mechanics. It's field theory. It's asymmetrics of the QCD. And that is a very important property of the NBS wave function, can be derived by using some Lippmann-Schwinger equation or something. However, we consider the information inside this interaction range and extract information about interaction for the atoms. So we define potential using following equation. Our potential is non-local, but energy or momentum independent, defined from this, defined from the NBS wave function using this equation. So this is the NBS wave function, and multiply free shading operator is 0, and subtract energy part. And outside interaction range, this is 0. But inside, this is non-zero. We parameterize this non-zero part is non-local potential uxy times phi ky, and integrate over y. This is our definition of this non-local potential. And important point is this non-local potential, even though it's non-local, it does not depend on k of the wave function. So you can see if we define local potential in this equation, this local potential may depend on k, like this. However, we convert this information into non-locality of ux and define ux with independently on k. And important point is, since we use NBA wave function, which has this asymptotic form, therefore, this potential is faithful QCD phase shift to delta LK. Therefore, if we have this uxy and solve Schrödinger equation, or maybe different Schrödinger equation, we can, from the asymptotic behavior, we can obtain information of the phase shift of the QCD. Of course, this uxy is not unique because of, since we restrict ourselves to the only elastic scattering. The potential may agree with elastic region, but may differ at inelastic region. We can construct many such potentials. I skip this. We can show such a uxy exists, but I skip it. But in practice, uxy is very difficult to treat or difficult to extract. So we introduce some approximation, so-called derivative expansion. And we expand uxy as local function vx and derivative. And at the leading order, we have local function like this, central or spin dependent, or so-called tensor force. S12 is called tensor operator, which defined in this way. And NLO, we have spin orbital force. And NMLO, we have second. Suppose we consider the leading order approximation, we can obtain this potential just multiply k minus h0 for the NBS wave function and divided by the NBS. And once we obtain potential, we can calculate phase shift and find energy below inelastic station. That is our strategy. And let me explain some advantage of our approach. In the RATS QCD, if we try to directly calculate binding energy, for example, we have to calculate 2 nucleon propagator, Nn, go to N bar, N bar, and Nn as a function of time. And this behaves like the sum of the exponential, like this. Ground state, excited state, etc. And if T is large enough, we can neglect higher order, higher excited state and obtain either. The problem is how large this T should be. And we know the excitation energy, since it's scattering, excitation energy is the scattering state, which momentum is 2 pi over L. Therefore, the energy is something like 2 pi over L squared divided by Mn. If, for example, if the volume is 4 centimeter, this splitting about 50 MeV. And if you increase volume, this splitting becomes smaller, and smaller, and go to 0 in the infinity volume. Suppose if we use 4 ferrite oxide, in this case, T must be much larger than this massive energy splitting, which is 4 ferrite, and is necessary to suppress higher order, higher excited state concentration. However, unfortunately, such a large time separation is difficult or almost impossible due to the back signal to noise ratio for the baryons. Signal to noise ratio suppressed exponentially in T with some prefactor like this. So it's very hard. So we need some small T evaluation. And skip this. And in the potential method, we can overcome this difficulty. So suppose we consider the 4-point function. This J is create two nucleons from vacuum, and this N and Nx plus R, and vacuum. This is what we call 4-point function. And if we put complete set in between this creation operator and annihilation operator, this can be written in the sum of the NDF wave function times some exponential suppression factor, plus inelastic contribution. But if T minus T0 is large enough, this inelastic contribution is suppressed. This scale is about 1 Fermi, so it's possible in current computational resources. And the problem is, as I said, if we are interested in this wave function at lowest energy state, we have to take T minus T0 very large to suppress higher order, higher excited state contribution. But our strategy is a little bit different. Suppose we consider this 4-point function divided by 2-point function square. Therefore, only differences appear this delta Wn, and delta Wn is energy minus 2mn. So it's kind of excitation energy from the threshold. And important point is our potential control all the scattering, elastic scattering state. Therefore, even though this red symbol depends on the state, this H0 and this U does not depend on it. And also we notice this Wn can be written Kn square, Kn is the momentum of this state, and Wn square. This is some simple mathematics. Therefore, we can replace this Wn with time derivative of this one, and this also Wn square is second time derivative, and this Kn using this definition is equal to U plus H0. So we have, using this sum the quantity R, we can derive the equation for the potential like this. So in other words, we use the excited state contamination as a signal, not noise. This is some typical result. This is first term, red one is first term, which determines the shape of the potential. And second term, correction term, is blue. And if only one state dominates, this term must be constant. However, because of the elastic excited state contribution, it's not constant. It depends on distance, R. And also third term, which coming from relativistic dispersion relation, therefore it's relativistic correction, but in this situation it's very small. It's almost negligible in this situation. And we finally obtain potential of this shape. This is the distance between two nucleons, and this is the potential energy in terms of MEV, like this. So this is our strategy and some typical result. Skip this because it's technical. And using that potential, that is some example, 2 plus 1 flavor QCD, that is spacing about 0.09 over 0.1 centimeter, and box size is 3 centimeter. But pile mass is rather heavy, 700 MeV. And this is a potential, and this is a singlet sector of NN scattering. This is a potential as function distance. And if you may know the phenomenological NN potential, qualitative future of the NN potential are reproduced in our calculation from LATS QCD. And using this potential, we can calculate scattering phase shift of this channel. This is our result. Shape, it has a reasonable shape compared to the experimental result. However, the strength is still weaker. And reason is, of course, due to the heavier pile mass, 700 MeV pile mass, core mass, pile mass. And we hope if we reduce pile mass under 140 MeV, this approach to this experiment.
Just one question.
Yeah.
In quantum field theory, we take into account quantum radiative corrections in quantum frequency. In this potential approach, no quantum corrections are included?
No, all quantum correction is completely included. So it's QCD result. It's QCD.
One more potential contain a higher derivative term.
Yeah.
In quantum is higher derivative term means a coupling constant has a negative mass dimension, and then Riemann model bit is not obvious.
No, QCD is renormalized theory. So its effective description of the low energy scattering. So it's kind of description, not fundamental theory. And one point is no di-neutron or maybe also spin triplet sector neutron at heavy pion mass is not bound. I mean, there is no bound state at heavy pion mass. And bound state, we think down state will appear if we decrease pion mass and to the physical term. Skip this. So I will give some recent result. One is some die-value search. Die-value is of course a bound state with value number 2. And in nature, only neutron is observed as a die-value so far. There are several other candidates. One is famous H die-value, which is UUDD-SS bound state. And also omega omega is 6 strange quark. And N omega, or maybe some people call delta delta, which is ABC effect. And some of them are investigated in our potential approach, and I will show some recent results. So we consider omega omega. The result is already published in archive. This calculation is in 2 plus 1 flavor QCD at almost physical power mass, 145 MeV, using K computer in Kobe, at Kobe in Japan. And lattice spacing is about 0.09 centimeter, and box size is huge, 8 centimeter box size. This is omega omega potential. This T is T in the NBS wave function, and we need relatively large T to suppress inelastic contribution, but we don't need huge T to suppress elastic contribution because we can use elastic contribution as a signal. So potential is almost T independent at this range. Therefore, we can use this value of T, and we observe some strong attraction appear here. And using this potential, we solve Schrödinger equation and calculate scattering phase shift. So scattering phase shift as a function of energy is something like this. So this is phase shift start 180 at pi. Pi means there exists one bound state at negative energy. And this is also, this change is very strong. That means its region so-called unitary region, liquidity of the bound, or if interaction is a little bit smaller, it becomes unbound. So it's liquidity of bound unbound state region, which is called unitary limit of this. Maybe it's related to the first talk of this morning session. This is one of the QCD example of the unitary limit. And we calculate, of course, we can calculate binding energy using some method, and found of the binding energy of 1.5 MeV, very, very tiny binding energy, and size of the wave function is about 3 centimeters. It's root mean square of distance of the wave function. Of course, the omega has charged, negatively charged particle. Therefore, we have to consider Coulomb interaction. And it's easy, just we put Coulomb potential in between 2 omega, and we obtain this result. So binding energy is reduced because of the Coulomb repulsion and becomes half of this, about -0.7 MeV. And the size is a little bit increased because, again, Coulomb repulsion. And, but this suggests there might be some bound state of 2 omega. We call this is most strange divarium because it contains 6 strange quarks. Similar calculation has been done for N omega. In this case, interestingly, there is no repulsion. What we call short distance repulsion is repulsive core. There is no repulsive core because N and omega doesn't share any same quarks. So therefore, there is no Pauli blocking effect at short distance. And we get this attractive potential and calculate phase shift. And it's k cotangent delta plotting. And again, so this is 0. Therefore, this part gives 1 over scattering length. So, and scattering length is negative in particle physics convention. That means there would be bound state around some energy region. Therefore, there exists some bound state. And we did not calculate binding energy at this moment, because it's very preliminary. But this N omega, this is omega is a lot of omega produced in heavy ion collision. They may found some strong correlation between N and omega in the data of the heavy ion collision. This is some interesting investigation in experimental one. And this is not physical point calculation, and we are now performing at QCD N omega potential calculation at the physical pipe, and we'll publish result in the future. Third one candidate is H divarium. I repeat. I will make some brief introduction of this part and go to exotic hadron because of time constraint. Again, this is UUDDSS calculation. But however, strange quark is heavier than UU and DD. Usually analysis is very complicated. So we first consider the ideal situation. That means flavor SU3 limit. That means U and D and S has the same mass. Flavor SU3 is exact in this case. And in this case, there are 6 types of calculation. And H divarium corresponding to flavor singlet part of the potential. And this is the flavor singlet potential. And as you can see, again, there is no repulsive core or repulsion at short distance, and the force is attractive at all distance, and it suggests existence of bounds. And also, we check volume dependence from 2 to 4. It's almost independent in volume, in particular between 3 and 4 femtometers. And we use 4 femtometer potential and fit it and solve the Schrödinger equation. And we found one bound state, which is mixture of lambda lambda, NZ, and sigma sigma. So it's like UUDDSS bound state. This is a binding energy and also size of the bound state, and other several value of the pion mass. Since it's flavor SU3 limit, pion and kaon have the same mass, and we call it pseudoscalar meson mass. If it's very heavy, binding energy is about 50 MeV deep. But if you decrease pion mass from 1,000, 800, 700, 500, and the binding energy decreases, but not so rapidly. It's about lightest one minus 30 MeV, and the size is like from 0.7 to 1.3. And the result, our result is summarized as follows. And H divarium exists in the flavor SU3 limit, and binding energy is 25 to 50 MeV at this range of Coke mass, and the Coke mass dependence is rather much. But of course, question is real world, and because of time constraint, I skip the what happened in the real world. But if I will have a remaining time, I will come back to this point. However, the one point is in this H divarium is compared to deuterons, the potential and wave shape of wave function are rather different. The H divarium is rather compact object compared to the deuterons. So I've changed the subject. Okay, 10 minutes. Consider exotic hadron candidate. Let's see 3900. So this is germanium-like state. So let's consider germanium spectrum. And Coke model will describe the observed mass spectrum below 3.8 GeV. So this black one is Coke model prediction, and blue square is the experimental value. So it's Coke model prediction is very well. But several states above 3.8 GeV are not discovered. For example, this triangle one are not observed in experiment. Instead, some new state people called X, Y, Z, not predicted by Coke model, are experimentally observed, like Y here, red one, or ZC3900, or X. Like. So people may say this might be exotic state. But important point is all new states are found above 3.8 GeV, and lowest open chance threshold is this d bar d. That is, sorry, 3.75 GeV. And all new states are embedded in the two meson continuum, like d bar d, d bar d star, d bar star, d star. So they are out of open channel to meson state. Therefore, channel coupling is very important to understand nature of X, Y, Z state. So, and let's consider tetracoke candidate ZC3900. So this is observed decay of Y. It's another exotic candidate. It produces E plus E minus collision, this state is produced, and decay to pi, and this ZC3900, and this state decay pi and j psi. This is invariant mass of pi j psi and number of events. And this is base 3, and this is bare. And they observe some peak around 3.9 GeV. And they fitted this peak as a Bright-Wigner form and obtained mass is 3900 and width is 60 MeV. And this is just above d bar d threshold, 3.8 something. And there are several interpretations of this state. One is tetracoke. It's C bar C U D state. And the other is, for example, the J psi pi atoms, D bar D molecule. It's a G3 corresponding to some Jungian state. But the other interpretation is it's just D bar D threshold kinematical effect. So it's kinematical origin, not state, Jungian state. So there are four different interpretations. So to determine the origin of this state or this signal, we perform lattice QCD calculation, which is so-called coupled channel potential method for this state. This is a guy to take care of this calculation. And as I said, there are many two thresholds. It's lowest is pi j psi, low eta c, d bar d star, and z appear here. So we have this d bar star, d star threshold. Therefore, we have to consider these three states and 3 by 3 potential matrix VAB. AB is either these three states. So it's 3 by 3 matrix potential. So this is result. We consider 3 pion mass from 700 to 400, 3 pion mass. And this is diagonal path. And you notice diagonal path is very weak and almost Hawk mass independent. It's almost negligible, except some short distance pieces. And also, this transition potential is very, very small. And this smallness can be understood the heavy Hawk symmetry, because to change this state this or this state this, spin of Chan-Hawk must be flipped. But since spin flipping interaction is 1 over m suppressed, and this amplitude is suppressed for Chan-Hawk. But on the other hand, this off-diagonal part has sizable contributions like this. And this transition is just Chan-Hawk interchange. So heavy Hawk symmetry does not prohibit this process. So this strong off-diagonal potential is important to our analysis. And so let's consider structure of this state. So we calculate first invariant mass distribution two-body scattering. And unfortunately, experimental is three-body because y decay to pi zc and zc decay to pi j psi or etc. So it's complicated, but we consider two-body scattering using our coupled channel potential. And amplitude, the mass distribution is proportional to the imaginary part of the scattering amplitude. And we can also calculate S matrix and extend it in complex plane and search the pole of the S matrix using our potential. If it's resonance, it should appear secondary Riemann sheet like this. So first, let me show result invariant mass distribution for pi j psi and d bar d star. And in both cases, some enhancement just above threshold d bar d star threshold is observed like this. And this large enhancement coming from the effect of strong off-diagonal part of the potential. If off-diagonal part is switched off by hand, the result appears as black this line. There is nothing happen for this channel, and very small things, small contribution appeared in this channel. And also we notice peak is not bright Wigner shape, very strange shape. And the question is that this ZC3900 is conventional resonance. And to answer this question, we search the pole position of the S matrix. Of course, it's a little bit complicated because there are 3 thresholds, there are 8 Riemann sheets, and if ZC is resonance, they should appear second, or channel is the second Riemann sheet of this case. However, what we found is pole is below this d bar d threshold, not around near this point, but found pole around here. And therefore, this pole corresponding to so-called virtual state. And we also estimate, calculate pole contribution to the scattering amplitude, and this is very small. So because it's far from real axis. Therefore, our conclusion is that ZC3900 is not a resonance, but a threshold cusp induced by strong channel, off-diagonal channel coupling. That is our conclusion. And because of time constraint, so just summarize our my talk. currently the RQCD potential method is the only way to investigate baryon interaction reliably in lattice QCD to avoid problem of the elastic scattering state. And the nuclear potential, hyperon potential, and more can be calculated in our framework. We found shallow bound state for omega-omega channel at physical pion mass. And H dibaryon is bound at flavor SU3 limit. Although I didn't show that we found H dibaryon becomes resonance with flavor SU3 flavor plate. And the physical point simulation is ongoing on this channel on K computer. And I show also application to exotic hadron, ZC3900, and our conclusion is just threshold effect, not the state. Other application is low or sigma resonance, heavy baryon, tetraquark, pentaquark, three-body force, etc. Also, we invested such a subject. This is our collaborators, my collaborators. Thank you very much.
Thank you very much. Now time is open for questions.
The first question is concerning the dibaryon of omega-omega state.
Yeah.
I think phase shift is not direct observable. So there's it can be manifested by the cross section. Omega-omega scattering.
Omega scattering in experiment. I think it's very hard.
Experiment all the lattice QCD, right, for the cross section. Right?
Cross section is this is phase shift, so it takes sine square delta.
Okay.
We get some. It's not difficult.
And another question is how to distinguish the cusp effect and the genuine.
Yeah.
And the cusp effect is only seen in very short region, like it's KEV, right? And it's cusp.
Sorry, I may use wrong word cusp, but some threshold effect. But point is, in our approach, we can calculate S matrix. Therefore, we can consider pole position. And question: this pole contributes to the amplitude one. That is very defined question, and we can answer.
This is the last question.
Do you have results on X3872? X3872?
No, we didn't.
Will you? Are you planning to?
Not definitely, but we now start to investigate the exotic in general. So maybe one of the, if you have some good information, please let me know. That might be.
Just like to hear your comment. I mean, we hear a lot of exciting thing about black hole and neutron star merger.
Yeah.
I wonder if lattice QCD could help us to learn about equation of state, other than just spectrum is interesting, of course, but maybe we can do something more.
Direct lattice QCD calculation is difficult because of the solver sign problem. So our strategy is to construct interaction of hadron and baryon including hyperon and give it to the nuclear physicist, and they calculate equation of state using that.
So this is input they can use to.
Yeah.
Okay.
So it's indirect.
So something concrete has been obtained, or is?
Yeah, there are some data.
Okay.
Okay, let's ask to speak again. Next speaker is from NTU in Taiwan. And his talk title is Addressing B2FL Anomalies with Minimal Flavor Violating G-prime boson.
Okay, so I'd like to thank the organizers for giving me the opportunity to give this talk.